You are falling. Right now, in this exact moment, not toward the ground, not toward anything you can name. There is no wind, no sound, no sense of speed at all. And that is the terrifying part, because when you are falling through nothing, there is nothing to tell you. It has already begun. Somewhere in the black distance ahead, something is waiting, something so strange. It forced humanity to rewrite the laws of physics just to explain it. You don't know its name yet, but you're already inside its story. Pull back far enough, and you start to understand. This isn't empty space. It's the opposite of empty. Somewhere ahead of you, there is more mass than our entire sun, crushed into a single point, smaller than a city. Its gravity is so extreme that even light itself, the fastest thing in the universe, cannot escape. That's why it looks black, not because there's nothing there, but because everything there is hidden from us forever. For almost all of human history, we had no idea this was even possible. We charted the stars. We named the constellations. We built entire civilizations around the night sky. But the thing that terrifies you right now was completely invisible to every person who had ever lived. For thousands of years, humanity looked up and never knew it was there. So how do you find something that gives off no light at all? How do you prove the existence of a shadow with no source? The answer came earlier than you might think. In 1783, decades before anyone had ever spoken the words black hole, an English clergyman named John Michell sat down and did the math. He discovered that if a star became massive enough and dense enough, its gravity could become so powerful that even light could never escape. He called it a dark star. There were no telescopes powerful enough to prove him right. He simply trusted the numbers, and the numbers were telling the truth. It would take more than a century and one of the greatest minds humanity has ever known to explain why John Michell's extraordinary idea wasn't just possible, it was inevitable. In 1915, Albert Einstein changed the way we understand the universe forever. Gravity, it wasn't a force pulling objects together, it was space and time bending. Imagine placing a bowling ball on a stretched sheet of fabric. The fabric sinks. Then roll a marble nearby. It doesn't move in a straight line. It follows the curve. That's gravity. Not a pull, but a fall through the invisible fabric of space and time. And hidden inside that beautiful idea was one of the greatest mysteries in the universe. Einstein's equations were beautiful. They were also, by his own admission, nearly impossible to solve. They were so complex that even Einstein believed nobody would find an exact solution for years, maybe decades. It took less than a month. In the winter of 1915, a German physicist named Karl Schwarzschild was serving on the Russian front during the First World War, and somehow, between the mud, the freezing cold, and the constant sound of war, he solved them anyway. Not an approximation, not a guess, an exact solution. He mailed it to Einstein from the trenches. Einstein was stunned, but hidden inside Schwarzschild's elegant solution was something neither of them truly understood yet. A single number, a single distance, And at that distance, the equations didn't just bend, they broke. Here's the simplest way to understand what Schwarzschild found. Every object with mass has what's called an escape velocity. It's the speed you'd need to break free from its gravity completely. For Earth, that's possible. We do it every time we launch a rocket. But Schwarzschild discovered something extraordinary. If you could compress an object enough, squeezing all of its mass into a small enough space, its escape velocity would keep rising higher and higher until even light itself could no longer escape. That distance now has a name: the Schwarzschild radius. Cross it, and there is no way back. Every star you have ever seen is fighting a war. On one side, gravity, relentless, patient, pulling everything inward. On the other, nuclear fusion, pushing back with unimaginable power for millions of years, sometimes billions. The battle ends in a draw. The star shines, it burns, it lives. But fuel never lasts forever. And when a massive star runs out of energy, everything changes. The outward pressure doesn't slowly fade away. It disappears almost instantly. And gravity, which has been waiting all this time, finally wins. The star's core collapses inward at an incredible speed, crushing itself in less time than you can imagine. As the star's core collapses, something extraordinary happens. The outer layers are blasted violently into space in a supernova, one of the most powerful explosions in the universe. For a brief moment, a dying star can outshine an entire galaxy. But that explosion is only the beginning. Hidden deep inside the collapsing core, gravity refuses to stop. If enough mass remains, nothing in the known universe can hold it back. It keeps collapsing, smaller and smaller and smaller, until it crosses its own Schwarzschild radius. And in that single instant, silently, invisibly, without a flash, without a sound, a black hole is born. Somewhere in our galaxy, it may have already happened, and we simply haven't seen it yet. We've talked about the event horizon as an equation, a boundary, hidden inside Schwarzschild's mathematics. But now, it's real. Imagine sending a scientific probe toward a newborn black hole. Its cameras are still transmitting. Everything seems normal at first, but as the probe gets closer, something impossible begins to happen. From our point of view, it appears to slow down, not because it's losing speed, but because time itself is slowing down. Its signal grows weaker, redder, and fainter until it seems to freeze forever at the very edge of the black hole. But on board the probe, nothing feels different. There is no wall, no barrier, no warning. It simply keeps falling forward to completely different realities, describing the exact same moment, and somehow both of them are true. So, let's finish what we started. You cross the event horizon. There is no flash, no sound, no feeling that you've crossed any kind of line. If anything, the silence becomes even deeper, but gravity is no longer playing fair. Here's something most people never realize. Gravity doesn't pull equally. Near a black hole, the force pulling on your feet becomes much stronger. than the force pulling on your head. Your body begins to stretch longer and longer, while at the same time being squeezed from the sides. Scientists actually have a name for this: spaghettification. It sounds almost ridiculous until you understand what it really means. Around a stellar black hole, this wouldn't begin. After crossing the event horizon, it would already be happening long before you ever reached it. But for the giants, everything changes. For the largest black holes, everything changes. Their gravity is spread across such an enormous distance that crossing the event horizon might feel completely ordinary. No impact, no flash, no warning. You simply keep falling deeper and deeper into darkness toward a destination you can never see. But to the universe outside, your journey has already ended. Your image remains frozen at the edge of the black hole, growing dimmer, redder, until it slowly disappears. Yet, from your own point of view, time continues exactly as it always has. You are still alive, still falling, still watching the universe disappear behind you to completely different realities the very same moment. Both completely true. And there is only one direction left: forward. Every equation that has ever described a black hole leads to one place: the singularity. According to Einstein's theory, everything that collapsed is compressed into an impossibly small point, a place where density becomes unimaginable. But here's the problem: whenever physics predicts infinity, it usually means our understanding has reached its limit. Most scientists do not believe the singularity is truly infinite. They believe it marks the point where Einstein's theory can no longer describe reality. Beyond this point, something else must take over. Something we still do not understand. The singularity isn't just the center of a black hole. It is the edge of human knowledge. For decades, scientists believed black holes only consumed. They never gave anything back. Then, in 1974, a young physicist changed everything. Stephen Hawking proposed an idea so extraordinary that it transformed our understanding of black holes forever. Empty space isn't truly empty. Tiny particles constantly appear and disappear in the quantum vacuum near the event horizon. Some of those particles can be separated. One falls inward, the other escapes very slowly. The black hole begins to lose a tiny amount of its own energy. It is called Hawking radiation, which means black holes are not completely black after all. Quantum mechanics makes a very different promise. Nothing in the universe is ever truly lost. Information doesn't simply disappear. It changes. It transforms. But somewhere inside every black hole, that promise begins to break down. If a black hole slowly evaporates and eventually vanishes completely, what happens to everything that ever fell inside? Every star, every atom, every secret the universe ever gave to it. Does that information still exist? Or has it been destroyed forever? For more than 50 years, some of the greatest minds in physics have been trying to answer that question. And even today, nobody knows who is right. Einstein's universe tells us one story. Quantum mechanics tells us another. Perhaps they are both waiting for a theory that has not yet been written. For most of human history, we believed black holes were eternal. Once they were born, they would exist forever. Nothing could escape them. Nothing could change them. They would simply wait in the darkness until the end of the universe itself. Then Stephen Hawking showed us something extraordinary. Black holes are not immortal. They are slowly disappearing, not in years, not in centuries, not even in billions of years. The largest black holes in our universe will survive longer than the stars themselves, longer than galaxies, longer than almost anything we can imagine, and yet they will die. One day, the last black hole will emit the last of its energy and quietly disappear into the darkness. No explosion, no warning, no witness. After all this time, it will simply be gone. Black holes are not rare accidents of the universe. They are everywhere, at the center of almost every galaxy we have ever observed. Something enormous is waiting, not millions of times the mass of our sun, but billions. These are the giants of the cosmos, supermassive black holes so large that their event horizons could swallow entire solar systems, and somehow they helped create the universe we know today. Without them, galaxies might never have formed as they did. Stars like our sun might never have existed, and neither would we. For something that destroys everything it touches, black holes have spent billions of years helping to create something extraordinary. Us, perhaps the greatest monsters in the universe, have been protecting its greatest masterpiece all along. At this very moment, we are traveling through space together. The Earth, the Moon, the Sun, every planet in our solar system. All of us are moving around something we cannot see. At the very center of our galaxy lies Sagittarius, a supermassive black hole containing millions of times the mass of our sun. And for billions of years, it has been there, watching silently as stars were born and galaxies evolved around it. It does not threaten us. It does not hunt us. Without it, the Milky Way would not be the galaxy we call home. Tonight, while you sleep, you will travel millions of kilometers through space around something almost impossible to imagine, and you will never even feel it. Black holes do not wander through the universe looking for worlds to destroy. They simply follow the laws of gravity, just as everything else does. And that is perhaps what makes them so unsettling. If one were to pass silently through our solar system, we would not hear it coming. There would be no warning sirens in the night sky. At first, nothing would seem different. Then, little by little, gravity would begin to rewrite the world we know. The planets would drift from their ancient paths. The night sky would slowly become unfamiliar. And long before we ever saw the black hole itself, we would feel that something was terribly wrong. The universe does not need violence to remind us how small we really are. For all that we have discovered about black holes, the truth is remarkably simple. We still don't know. We don't know what truly waits beyond the event horizon. We don't know what becomes of space and time at the heart of a singularity. And we still don't know how gravity and quantum mechanics become one. For more than a century, some of the greatest minds in human history have searched for these answers. And still, the universe remains patient. No matter how much we discover, there will always be something waiting beyond the horizon of our understanding. And that is why we continue to look up. For thousands of years, humanity has looked up at the night sky, searching for answers. Long before we understood the stars, we dreamed about them. Long before we discovered galaxies, we wondered what might be waiting beyond them. And long before we discovered black holes, we were already asking impossible questions. What is waiting for us in the darkness? Perhaps we will never know all of the answers. And perhaps that was never the point, because every question we answer gives birth to another waiting beyond the horizon of our understanding. That is why we continue to explore. That is why we continue to wonder. And that is why we still look up. For thousands of years, we have looked up at the stars, searching for our place among them. We have discovered worlds beyond imagination, listened to the echoes of the beginning of time, and learned that even the universe still keeps its secrets. And perhaps that is the most beautiful discovery of all. Not that we have found all of the answers, but that there are still questions waiting to be asked, because somewhere out there, beyond every horizon we have ever crossed, there is something extraordinary waiting for us to discover. And tomorrow, we will look up once again